You got it?
Yeah,
Okay.
it was a very, very simple question.
Okay, so let's go ahead and get class started here. Today we're going to start section 4.5. We're going to define and talk about inverse, sine, cosine, and tangent, and how to use those to solve trigonometric equations. Plus, we'll do some practice evaluating some inverse trigonometric functions. Claire, just so everybody can hear what your question was, Claire was wondering, how do you determine when you're doing a transformation of sine, cosine, or tangent, you're labeling the horizontal axis? When do you want to use fractions of pi, and when don't you? Well, if your period and your phase shift don't involve pi, you shouldn't be using fractions of pi when you label the axes. Okay, generally you only use fractions of pi to label the axes if your period involves pi. Okay, so anybody have any questions on the homework I just passed back, just to maybe go through one or two of them for clarification? 46. Okay, so the 4.3 homework, number 46, and was that a sketching one as well? Okay, so what was the function?
The function is g of t equals 2 minus 4 cosine t.
Okay, and it says probably find the
Amplitude and vertical shift.
okay, find the amplitude, vertical shift, and sketch a graph. Okay, well, first thing you need to do is rewrite this in the form CF of theta plus D. So you can rearrange the terms and get minus 4 cosine of t plus 2. I did see some people do 2 minus 4 to get a negative 2 cosine t, but that's not how this works. You're first taking cosine of t, multiplying by negative 4, whatever that value is, then you add 2. Okay? So when you rearrange terms, it's minus 4 cosine t plus 2, and I don't think there was really an issue with the amplitude or the shift, right? It was mainly just sketching the graph. Okay. So the amplitude's always the absolute value of the vertical shift factor. Okay, the amplitude's always going to be positive. I saw a few people write their amplitudes as negative numbers. You need to remember to take the absolute value of c. The absolute value of negative 4 is positive 4. And then the vertical shift is up or down. It's going to be up because of this plus 2. It's going to be up 2 units. Or if you like, the midline, and the middle value of this function is going to be positive 2. Now, did we do any horizontal transformations here?
No.
Okay, right? It's just a single input t. That's not being messed with. So there's no horizontal stretching or compressing, and there's no phase shift. So the period, I mean, I can write this down. The period p is still 2 pi, and there's no phase shift. Okay. Except there's one extra thing that you need to be careful of. So what transformation have I not mentioned yet?
The vertical reflection.
Yes, c is a negative number. So there's a vertical reflection. So you can say since c equals negative 4, that's less than 0. Okay, there is a vertical reflection. Okay, so what I'm going to do is, there's no phase shift, the period is still 2 pi. I'm going to look at my fundamental cycle of cosine before transforming. So there's the theta axis, or if you like, it's the t axis if we're looking at cosine t. Okay, now every time I graph, whether it's the original function or a transformation, you're going to see this pattern of the period gets broken up into fourths, 4 equal intervals that are each 1/4 of the period. Okay, so you would always start at your phase shift and then keep adding the quarter of the period until you've done that 4 times, and now you have an interval with its length being the period. Okay, here's positive 1, here's negative 1. Cosine starts at a max. Quarter way through the period, okay, any of these functions a quarter way through the, or for any transformation of cosine of t, a quarter way through a period, you're going to always be at the middle value. And then halfway through the period, you're at the minimum. Another quarter way through the period, you're at the middle value. And another quarter of the period, you're to the maximum. Now, come over here. There's been a vertical reflection. So the vertical reflection is going to change the graph as follows. If you reflect this thing over the vertical axis, now our fundamental cycle is going to look like the red graph. Okay, so when I'm graphing my fundamental cycle of this g of t over here, it really starts at a minimum value and then increases to a max. Okay, so let's go ahead and sketch this. I'm only going to draw one cycle. Let's see, the middle value is 2 and the amplitude's 4. So I think I need more distance on the positive vertical axis. I'll go 1, 2, there's where my midline is. And then I'll go up 1, 2, 3, 4 units to get to the maximum of 6. And starting at 2, I'll go down 1, 2, 3, 4 until I get to minus 2. That's going to be your minimum value. And then the period is still 2 pi. There's no phase shift, so our cycle begins at 0. And then I take my period and I divide it into fourths, which in this case is pi over 2. Okay, so I've got increments of pi over 2. And since there's been, usually a cosine graph starts at its maximum value, but since there's been a vertical reflection, you're going to start down here at negative 2 at 0, because there hasn't been a phase shift, so our cycle starts on the vertical axis. Quarter way through the period, you're at the middle. Halfway through the period, you're at the max. 3/4 of the way, you're back at the middle value. And finally, one full cycle gets you back to the minimum value. Here is one cycle of g of t equals 2 minus 4 cosine of t. Yes?
So you use the period to determine like the fractions going to be on the graph?
Yeah, I mean, whatever my period is, if your period involves pi, then your labeling on the axis will also involve pi. And what I did was, since there hasn't been a vertical shift or a vertical stretch or compression, the period's still 2 pi. There's no phase shift, so your cycle starts at 0 and finishes through 2 pi units. Okay, and then I always break up my period into fourths. Well, if my period is 2 pi, 1/4 of 2 pi is pi over 2. So starting where my cycle begins, I add pi over 2 once. I add pi over 2 twice. I add it a third time, and once I've added pi over 2 a fourth time, that brings me through a full cycle. Okay. And yeah, if in this case, since my period involved pi, okay, I'm going to have pi fractions on my horizontal axis.
If you had like a phase shift in terms of pi and the period in terms of like a just
yeah, if it's mixed,
integer.
so like what if your phase shift is doesn't involve pi, but your period does,
what would you
for
do
instance? I think there was one homework problem.
It was, yeah.
52 is a good example. It's 1 minus 1/2 sine of, inside the parentheses, it starts out as 4 minus 2 theta, and then I believe nope, I don't have a plus 1 out here. So 52 is this. The directions say just find the amplitude, the phase shift, the vertical shift, and the period. And then it says use the interactive figure to sketch a graph. And my directions were drop a hand. I was generous if people didn't actually draw the graph for this particular problem. Now, what I would do is rewrite this in the form c sine a theta minus b plus d. Okay. Before I do anything, we'll rewrite it. So first of all, rearranging the first two terms, and then rearranging the terms inside the parentheses, you get minus 1/2 sine of negative 2 theta plus 4, and then plus 1 on the outside. And then one more step. You have to factor out the negative 2 to make the a appear in front of the theta minus b. So it's -2 theta minus 2 plus 1. And one more little trick. You can ignore this or you can use it. If you reflect sine horizontally and then vertically, nothing happens. Okay, your cycle, it's going to look like exactly the same graph. Or you can use the fact that sine is an odd function. This negative can be pulled up front. Okay, I like to think of it that way. Okay, so 52, you could have simplified it down to 1/2 sine 2 times theta minus 2 plus 1. Okay, and here's what I'll do. Okay, so the amplitude is 1/2, the midline was y equals 1. The period is 2 pi over the absolute value of a, which is 2 pi over 2. So that's a case where the period's pi, but the phase shift is 2 units right. Okay. So yeah, now you've got a mixture. Your period involves pi, but your phase shift doesn't. And I'm just going to be a cheater. I'm going to use a break in the graph to kind of ignore the difference. It's kind of hard to compare pi to a whole number increment like 1 or 2. So what I do when I graph this, and I'll let you do this, put a break in the graph. That basically says ignore this distance. We don't really care what it is. Okay, and then what I'll do is I'll just come over here. My cycle begins at 2. And if I add pi to it, that's where my cycle ends. So my cycle would end at 2 plus pi. And then I'll just cheat right here, and I'll break this up into fourths. This would be 2 plus pi over 4. Okay, I'm just dividing my period by 4, adding it to my phase shift once. The middle one would be 2 plus pi. This one would be 2 plus 3 pi over 4. And if you add pi over 4 one more time, you get to 2 plus pi. So that's one thing you can do. Just cheat a little bit and draw a break in the graph. Has anybody seen that before? Like, what if you have a function that starts at like 3,000 or something like that? You can always put a break in the graph and go 3,000, and then just go 3,001. Obviously, this is not 1 unit, right? It's 3,000 units. The break there is just saying let's ignore that distance and let's just start our graph at 3,000. Same thing over here. I'm just going to put a break in the graph, ignoring what this distance really is. And I'm just putting a break there. And okay, I'm starting at 2. My period is pi. I add pi to that. That'll give me 1 cycle. And then I'm splitting that interval into fourths by adding pi over 4 every time. So that's what I would do there. And then let's see, here's +1, here's 1.5, here's 0.5. We knew the midline was 1. And since there's no reflections or anything, sine starts at its middle value. Quarter way through the period, you're at a max. Halfway, you're back at the middle. 3/4 of the way, you're at a min. And finally, through a full period, you're back at the middle value. So there's 1 cycle of that function. Okay. So just exploit breaks in the graph if your phase shift if your phase shift doesn't involve pi but your period does, or vice versa, you can just kind of cheat like this a little bit. You could do it the other way too. If your phase shift, let's just pretend. So if I just, without identifying a function, if my phase shift this time is pi units right, but my period p is equal to 2, I would just do the same thing. I'd say, okay, there's pi, ignore the units from 0, and then we're done at, well, my period's 2, I just go to 2 plus pi. This is an interval now of width 2, and then I can break it up into fourths. This is pi plus 1, pi plus 1/2, and this is pi plus 3/2. Okay, so I'll let you do that. Okay. And then it depends on what the amplitude and everything else is. Okay. So that's what I would do if you have a mixture of pi units and non-pi units for your period or your phase shift. shift and vice versa. They're not going to show you that in the textbook because the textbook is using technology. They're actually going into a computer graphing program and plotting these functions. So they're not actually graphing them by hand. Okay, but exploit breaks in the graph if you have to make it easier. Does that kind of help or answer that? Okay. All right, so I want to go ahead and get started. Let's see. Any homework I have is for coaching.
She needs a 4.5.
I'll get one for her. Anybody else need a 4.5 handout? Did I miss some people? No. Oh, I can't read. Oh. I'll take one. Did you get one, Osha?
Yeah.
Okay. So inverse trigonometric functions. Now, before we go in and define inverse trig functions, I think it'd be a good idea to maybe spend a few minutes reminding everybody what an inverse function is, when a function has an inverse, how it alters the domain and range. So real quick, we'll go through that. So I'll start with, so this is 4.5 inverse trig functions. And then a little spiel on inverse functions. Okay, so, and I think I just wrote this down for everybody. If a function is 1-to-1, and how do you know if a function is 1-to-1? From pre-cal 1, it has to pass the, I'm just going to write horizontal, HLT for horizontal line test. So a 1-to-1 function, one that passes the horizontal line test, f, okay, has, I think we need to say it this way. Did I say with domain D and range R, has a unique inverse. And remember, the notation for the inverse function was f with a superscript -1. Remember, that does not denote a power like it does for a real number. Okay? A number to the -1 is notation for the reciprocal. A function with a -1 power is just notation for the inverse function. So just make sure you're not mixing up reciprocals and inverse functions. So there's a unique inverse f to the -1 with, and then what does an inverse function do to your domain and range? It swaps them. The range of the original becomes the domain of the inverse. So the domain of f inverse is R, and the range is D, with domain R and range D. And the property is, so I'll write such that f inverse of y is equal to x. So I'm telling you how to define the inverse. Okay. When the inverse is y and the output is x, that happens whenever f of x equals y in the original function. Okay. So what an inverse does is the inputs and outputs of the original function get swapped when you go to the inverse. The output is now the input, and the input is now the output. Okay. A little note, this last part also says, okay, so that's the same thing as saying if xy is on the graph of f, then y comma x is on the graph of f inverse. Okay. This is the function notation that expresses that. If f of x equals y, xy is on the graph of f. And then you swap the input and output, that means the point y comma x is on the graph of f inverse. Okay. If you struggle with inverses, I suggest you go back and review them in section, I don't know, I think they're in chapter 1 of our textbook somewhere. Okay. Yeah?
If you didn't take pre-cal class, excuse me, if you didn't take pre-cal class quarters, is it still going to be on the book, or is it
Yeah, it's in our same book.
It's in the same
Yep,
book.
it's somewhere in chapter 1. So if you're in our book and you go click that little chapter, there's a little tab you can click that brings up all the sections. One of the sections is inverse trig functions. Now, you should be able to survive, with minimal knowledge about it. What I've told you here should be enough to survive this section, but if you want just a little deeper understanding, just to kind of shore things up, I would make sure to take a look there. Yeah, it's just that we don't have a whole lot of time to go back and review it all. Okay. Pictorially, I can also write this. I mean, here's a set right here. Here's a set right here. Let's call this the domain. So this is going to be the set D. That's the domain of F. This little blob over here is supposed to be the range R. If you take a little input here, so take an X in the domain, F is going to take you to a point F of X in the range. Okay. But this F of X is now in the domain of the inverse. So what the inverse function is going to do is this going to bring you back where you started. Okay. So one of the properties that's true, this won't be true for our trig functions all the time. So those are two properties that are true for inverse functions. Okay. Again, you might have to review function composition from chapter 1 as well. This just says if you plug x into f and plug that back into the inverse, you get back to where you started. The way I like to think of it is the inverse function is kind of like tying and untying your shoes if you compose them. Right? If I tie my shoes and then untie them, I get back where I started. Okay. Other operations that are inverses of each other are the square root function and the square function. Okay, a square root is the opposite of doing a square. Okay. All right, so using this idea of one-to-one, okay, I don't know if this diagram, there's a nice interactive figure in the textbook with a diagram like this if you want to go read through it, but I don't know how important it is or not. But we're going to construct inverses of sine, cosine, and tangent. The main thing is that a function has to pass the horizontal line test to have an inverse. So let's start by, I'm going to graph sine. Okay. You might need to write this on an extra note sheet. I don't know if I left you enough room in the handout. So what does the graph of y equals sine of x look like? So here's instead of using theta, I'm using x and y for the coordinate axis. Okay, so I'm going to go 2 pi units to the right. I'm going to go 2 pi units to the left. So I'm going to do 2 cycles. Pi over 2, pi, 3 pi over 2, minus pi over 2, minus 3 pi over 2. And then here's positive 1 and here's negative 1. And that's my terrible graph of sine, but I think it's good enough. Okay. What's the first thing you notice about sine if you try and think about the horizontal line test? Okay, so Chris, you said this isn't going to pass the horizontal line test. So sine does not have an inverse over its entire domain. Okay. So this graph, sine on its entire domain fails the vertical line test. So what actually I care more about is what I'm going to call the restricted y equals sine of x, where the domain is really going to be minus pi over 2 to pi over 2. Okay, so if you notice, if I get rid of the stuff to the left of pi over 2, and I get rid of the stuff to the right of pi over 2, is this graph going to pass the horizontal line test?
Yeah.
Okay, so the only way to get an inverse for sine or cosine or even tangent is you have to restrict the domain to a piece of the graph that passes the horizontal line test. Now, this was not the only interval I could have used, but traditionally it's what people do. I could have also restricted the domain in a lot of ways. I could have gone from pi over 2 to 3 pi over 2 instead. Okay. So this is going to be the restricted sine function with domain minus pi over 2 to pi over 2. The range is still going to be minus 1 to 1. Notice you still have minus 1 as a minimum value and positive 1 as a maximum output value. Okay. Now, who remembers another way to graph an inverse? Okay, so you can take all the points on this graph and you can swap inputs and outputs. Okay, let me see if I can do that without screwing this up. So somewhere on the vertical axis, let's say about, can someone slap pi over 2 in their calculator real quick? It's like 1.6 something, I think. 1.57. Okay, so it's about half a unit up from here. So here's pi over 2. And then I'll go about another half unit down. Here's minus pi over 2. And then positive 1 and negative 1 are going to be about right here and right here. It's kind of tough to do this, but this point pi over 2 comma 1 now becomes the point 1 comma pi over 2. So this is that idea of taking a point on the original graph, swapping x and y coordinates to get points on the graph of the inverse. And then now, this point right here is minus 1 minus pi over 2, which when you swap coordinates becomes minus 1 minus pi over 2. And then I got to think now how this works. I don't really like drawing these on the same set of axes. I think the graph of the inverse is going to look something like this. I think that's right. If you imagine reflecting this blue graph over the line y equals x, and then this red graph is going to be y equals sine inverse of x, or there's a second notation. Sometimes people write arc sine. Okay. So another way to get the graph of an inverse is to reflect it over the line y equals x. And what's the domain of arc sine or the inverse going to be? You take the original domain and range and you swap them. So the domain is now minus 1 to 1, and the range becomes minus pi over 2 to pi over 2. Okay. The textbook probably has a much better picture. Yeah?
On the test, are you going to want us to do 2 different graphs?
I don't think you should ever really need to graph inverse sine. I'm just showing it to you just so you see it once. But I don't think I'll ever really make you sketch the graph. We're really just going to use the function itself to solve some things. Okay, so the main thing you need to remember, though, is the domain and range and what the form that you write it in is. Okay, so to be able to get an inverse, you had to restrict the domain of sine to minus pi over 2 to pi over 2. And then the inverse function swaps domain and range. That should be enough to get what you need. Okay. Now, the same thing is true of cosine. I'm going to let everybody read it in the book, though. Okay, so make sure you read the textbook. They have actually a lot better interactive figures that compare the graph of cosine to its inverse. Much better than I could ever draw in class by hand. Okay, so what I'm going to do is, maybe I'll at least show you what the restriction of cosine is. If you want to see the graph of the inverse, you can look in class. But to get an inverse for cosine, you're going to restrict the domain from 0 to pi. So this is what I'm calling restricted, y equals cosine of x. So the domain restricts to 0 to pi, and the range is still going to be minus 1 to 1. Okay? And then, like I said, if you reflect this over the line y equals x, you will get the graph of the inverse. So again, I'll leave it to everybody to look in the textbook to see what the graph looks like. Okay, and then the function that's the inverse, you can write it as y equals cosine of x, or some people write arc cosine of x. Those are just notations for the same thing. And the domain is going to be -1 to 1, but the range becomes the domain of the original 0 to pi. And we'll do some practice calculating some values and see how they work in just a moment. Okay. And then one more. Okay. And then I'll actually, so this box down here, the definition, leave that like, I'm going to write something a little bit different than what I've written up here. Okay. This is an intermediate step to getting to my definition down here. And then finally, tangent, if you like. I'll show you the graph of tangent. I think this one's a little easier to draw both together. So remember, tangent has period pi, and two of the vertical asymptotes are at -pi/2 and pi/2. And there's the graph of tangent. You're going to see in a second why I'm putting pi/2 and -pi/2 on the vertical axis. Okay, so the blue graph up here, that's y equals tangent x. I guess we can call it the restricted version. With domain -pi/2 to pi/2. Okay, but the range, this little piece between asymptotes, goes down forever and up forever. So the range is all real numbers. This one's a little bit easier for me to draw. Basically, when you go to the inverse function, the vertical asymptotes become horizontal asymptotes, and then the inverse function looks like this. Let me make sure I don't screw this up. Yeah. Okay, so there's what tangent inverse would look like. Okay, so you have y equals tan inverse of x, or if you like, you can call it arctan of x. The domain is going to be all real numbers. And the range is going to be -pi/2 to pi/2. And then the only one I really skipped was cosine. Again, just make sure you look through the textbook. It wouldn't be that hard to just Google it either. You could just Google cosine inverse and it would probably show you a graph. Okay, now for the formal definition now, so the notation is a little bit different than what I've used up here. So this was just always writing the inverse as a function of x. Okay, and I just kept the dependent variable y. And let me let people get caught up before I go on. Turns out this does record even if it goes into sleep mode. Yeah. I think I can come erase this part. Okay, so for the formal definitions that you need to actually compute values of the inverse functions. So this is what I would write in a little box, if you will. Okay, so inverse, sine, cosine, and tangent. So definition here. So what I've written now is theta equals arc sine of y is the value of theta such that y equals sine of theta. Okay. And theta here theta is always going to be some angle between -pi/2 and pi/2. Okay. So if I want to do arc sine of some number between -1 and +1, the output is the angle that you need to plug into sine to get back that y value. We'll do some examples in a moment. The next one, theta equals arc cosine of x, is the value of theta such that x equals cosine theta, and theta is always going to be between 0 and pi, because that's the range of arc cosine. And then finally, theta equals arctangent of m is the value of theta so that, or such that, m is equal to tangent theta. And the angle, again, is going to be between pi over 2 and pi over 2, because that's the range of the arctangent function. It always spits out, the outputs are always angles between minus pi over 2 and pi over 2. Yeah?
So the reason that you have that, I'm just trying to make sense. So y equals sine of theta, and they did it that way because sine is the y value on the unit circle, or does that have no correlation?
No, that is going to be
Okay.
100% correct.
And so
Yep.
then for
So the reason they used y for sine is always the y coordinate.
Okay.
They used x for cosine because cosine of an angle is always the x coordinate.
and then the slope.
And then, yeah, if you've realized tangent theta is always y over x, tangent of an angle is always the slope of the terminal side of the angle. So that's why they're using m.
Okay.
Yep. Okay, now let's put this into practice. Okay, these definitions are nice and all, but if you flip the page over, let's actually compute some of these values. So how are we doing on time? We got 13 minutes. Okay, that should be fine. Okay, so let's see how this works. I want to compute arc cosine of a half. So arc cosine of a half is supposed to be the angle theta. Okay, so for now, just call arc cosine of 1/2 some angle theta, where if you plug that angle back into cosine, you get an output of a half, and it's supposed to be the angle, well, the outputs of arc cosine are always angles between 0 and pi. So here's where the unit circle comes in now. So arc cosine of a real number is always some angle. Okay, and if you plug that angle into cosine, you get the input of the arc cosine function. So all I've done here is I've taken my input and output and swapped them going back to the original. That's what inverses do. And the output of arc cosine is always an angle between 0 and pi. So now, on the unit circle, which quadrants am I going to look for angles if we're supposed to be between 0 and pi? So we're looking in quadrants 1 and 2. Although, which quadrant has positive cosine values? Just the first quadrant. Okay, so we're looking for an angle theta such that the x-coordinate up here is a half, and I don't really care what the y-coordinate is. It's sine theta, whatever it is. Although we know what that is, actually. I'll write it down. It's root 3 over 2. And what's an angle in the first quadrant where cosine is a half? Yeah, that's going to be pi over 3. Okay, so this implies the angle theta is pi over 3. So arc cosine of 1/2 is equal to pi over 3. Right? Pi over 3 is the angle between 0 and pi that you plug into cosine to get 1/2. That's it. So always call the output of your arc cosine, arc sine, arc tangent some angle theta. And then when you convert back to rewriting that in terms of cosine, We're looking for an angle between 0 and pi so that we get 1/2. Well, the only such angle is pi over 3. That's the value of our cosine of 1/2. Okay. But yes, that is it. Now if I switch the notation, so in part B we're going to use the other form. I want to find sine inverse of minus 1 over root 2. Now, I don't really need you to write this every time, right? I could say this is some angle theta, right? So this is going to equal some angle theta, where sine of theta equals minus 1 over root 2, and the angle this time we're looking for is between minus pi over 2 and pi over 2, coming from the restriction of sine to get a one-to-one function. So now looking at the unit circle, we're looking for an angle. Well, minus pi over 2 to pi over 2 has to either be in quadrant 4 or quadrant 1. Okay. However, sine is the y-coordinate of a point, and we have a negative value. So is my angle in quadrant 4 or quadrant 1? It's in quadrant 4. So my angle of theta is down here. It's going to end up being a negative angle. It has to be between minus pi over 2 and pi over 2. And the y-coordinate down here, I don't care what the x-coordinate is, but the y-coordinate's minus 1 over root 2. Okay. Now, anybody have an idea what this angle is? You can maybe just use an angle up here. Which is an angle up here that has a y-coordinate of positive 1 over root 2? What was the angle? Pi over 4 is the angle that has a y-coordinate of 1 over root 2. And then you were actually saying, so what would this angle be?
Negative.
So again, it has to be between minus pi over 2 and pi over 2. Yeah, so minus pi over 4. No, you're not wrong, Brandon.
I just have to go low. I have to just.
Yeah, instead of going the positive direction to 7 pi over 4, we're actually going minus pi over 4 units. So your answer wasn't wrong. It's true that sine of 7 pi fourths is minus 1 over root 2.
But it's not in the number.
But yeah, it's not in the range of arc sine. Yep. So the answer here is sine inverse of minus 1 over root 2 is actually negative pi fourths. Right? Instead of rotating positive pi fourths, we're rotating minus pi fourths. That just changes the y-coordinate from positive to negative. Okay. So that's it for that one. So you're saying what angle, when you plug into sine, gives you minus 1 over root 2, where the angle is strictly between minus pi over 2 and pi over 2. The only such angle is minus pi fourths. Okay. So help me out with this one. What about where tangent inverse is negative 1 over root 3? That's part C. Okay. So this equals the angle theta, where when you plug that angle into tangent, you get minus 1 over root 3. But again, remember the range of arctan. That angle has to be between minus pi over 2 and pi over 2. So I claim tangent of an angle is always the slope of the terminal side of the angle. Okay? That's another way of thinking of it. Okay? Another thing to observe is that tangent is only positive in the first or third quadrant. It's negative in the second or fourth. But since we're between minus pi over 2 and pi over 2, the angle has to be in the fourth quadrant. So there's my angle theta. And what's the only way to obtain minus 1 over root 3? Well, the x-coordinate down here would have to be a positive root 3 over 2. The y-coordinate would have to be negative 1/2. Because negative 1/2 divided by root 3 over 2 gives me minus 1 over root 3. And then, anybody know what angle would work there? So yeah, remember sine of positive pi over 6 has a y-coordinate of 1/2. If you reflect that over, that brings you to minus pi over 6. Okay, so that means tangent inverse of minus 1 over root 3 is negative pi 6. I guess another thing you can do is, don't you have that little table I made for you too? Right, you've got that table where you've got sine, cosine, tangent. And if you look at the pi over 6 piece, you get 1/2 root 3 over 2 and 1 over root 3. So for positive pi 6, tangent's 1 over root 3. Reflecting it over the horizontal axis brings you to minus pi over 6, which has a value of minus 1 over root 3. And then what do I have for the next one, for part D?
Not defined.
Sine of negative 2.
Okay. So what do you think about this one?
Not defined.
Okay. Who said that? Kirsten. Kirsten said this was not defined. Okay, we'll go back to my domain and ranges of arcsine. The domain of arcsine. So the range is minus pi over 2 to pi over 2, but the domain of arcsine is minus 1 to 1. Yeah, so that's not in the domain, so this is undefined. Make sure you're looking for that on your homework. Some of the problems will try and trip you up by trying to plug something into an inverse trig function that's not in the domain. Okay. So there's no work to be done there. And then finally, and depending on the time, we'll probably call it a day right here since we only have a couple minutes left. Tomorrow we'll start solving equations. Now, here's where things get tricky. Remember earlier I wrote on the board, if you compose a function with its inverse, you always get the input back? That does not work with sine and cosine necessarily. Okay? Because what's the range of sine inverse? Yeah, minus pi over 2 to pi over 2. Is 5 pi thirds in the range of arcsine? No, it's too big, right? So this will not just equal 5 pi over 3. Okay? So here's one thing I want you to write as a note before we solve this.